All right. The next thing we're going to look at is something called the extreme value theorem. Now that one isn't quite as obvious from the name what's going on here. And this is one of the most important in application. And we're going to use this a lot in a couple of weeks when we get to what are called optimization problems. The extreme value theorem, it's kind of a guarantee. Okay? It's kind of a guarantee. So let me give you a simple picture. So I've got some graph, and I'll do the one we did earlier. Really, really simple. If I take a closed interval, so think about just going endpoint to endpoint. Okay, I'm going to take a closed interval. Maybe I'm going to go from here to here. Okay, there's my A to B. I'm only considering this graph over this closed interval. Now, right now, does this graph have an absolute maximum? The graph? No. Does it have an absolute minimum? No. But what if I only go from A to B?
Yes.
I'll make it easier. Does this graph have an absolute maximum?
Yes.
Does it have an absolute minimum? Yes. So I'll tell you the conditions in a moment, but all things being nice, if I give you a closed interval, you're guaranteed an absolute maximum and an absolute minimum. If the conditions are met, we'll go over those in a moment. And the only places they can occur are at critical values or what? Endpoints. Which makes the calculation so much easier. Now, what are the conditions? Well, now I'm going to give you the conditions. F of x is differential over AB, okay? Actually, in this one, I don't even need to be differential. Let me back up. I actually only need to be continuous. I can have weird points. Continuous is not as strict as differential. It's differential over AB. That means you always define things. Continuous, differential, everything is always defined over an open interval. So let me change this. I'm going to make these both open. And I'm going to show you mathematically how to now say, and in words, the endpoints also exist. Here's the thing. This could be the endpoint of the function, or the function could go on forever. It doesn't matter. But the problem is you are not continuous at the endpoint of any function. Think of the square root function. You're not continuous at 0. Oh, so if the function itself has an endpoint, you're not continuous there. So I'm continuous over the open interval, and the endpoints exist. So, and, like this, the limit as x approaches a from the right of f of x is in fact f of a. What did I just do? I filled that point in. It does not matter now what's happening to the left of that point. And the limit as x approaches b from the left of f of x is f of b. So would you ever have a function where you had to worry about this? Yeah. They're really simple. This is the top half of a circle of radius 6. The domain is -6 to 6. Am I continuous at either -6 or +6? No, because they're endpoints. Oh, but am I continuous? Oh, can't spell. Am I continuous over the open interval, which would be, am I continuous from -6 to 6, not including the endpoints? Yes, I am. And now is the limit as I approach -6 from the left going to be 0? Yep. As I approach positive, or I should say from the right, as I approach +6 from the left, is that going to be 0? Yep. I now have met the conditions for the extreme value theorem. Do you notice that both of those points are actually endpoints of the function? I'm not continuous at the endpoints of a function. I was continuous over the open interval and the endpoints existed. So it did not matter whether there was anything to the right. That's the key thing here. A lot of the textbooks will just say you're continuous over the closed interval. You can't define continuity over a closed interval. It contradicts itself. And one of the worst things is in the Swakowski book, they actually use this example. And they say in this example, you're continuous at both endpoints, even though earlier they say you can't be continuous at the endpoint of a function. That's a major gaffe. But I'm continuous over the open interval and the endpoints exist. That's pretty much going to be not a big deal. I'm guaranteed an absolute max and I'm guaranteed an absolute min. And where must they occur? Well, first of all, between A and B, not outside, but they can only occur at critical values or endpoints. So here's the thing. I'm going to give you a function, I'm going to give you a closed interval. You know, something like simple like a polynomial. I'll give you a function, I'll give you a closed interval. I need to find out all the critical values, and then I just simply evaluate my function at all the critical values and the endpoints, and whichever one's the biggest y value wins. Whichever one's the smallest one, I guess wins the other prize, right? The minimum prize. That's it. I don't have to do anything else. It's actually quite simple. So let's do this. Let me come up with something relatively simple, okay? I gotta reverse engineer this real quick. All right, let's consider f of x equals 1/4, I'm sorry, not 1/4, sorry, x to the 3x to the 4th plus 8x cubed minus 48x squared minus 3. And the interval we're looking at, let's say, is the interval from -2 to 6. Okay, I think this will work. Hopefully I didn't mess this up. I would like to find the absolute maximum and the absolute minimum of that function over that interval. Does this require that I draw the picture, do you think? No. No. That's pretty much never going to be the case that you're required to draw a picture. I always tell everybody in every calculus class, you never have to draw the picture to answer the question, and then after every problem I like to draw the picture. So we know what our answer we just said. You can't use the picture to answer the question, but when you answer the question, the picture ought to confirm what you just said. It's a safer way of doing things, because you can't make things fit the picture. Especially because just think of the scale alone. The picture I come up with on Desmos doesn't look exactly the same because I'm not using the same scale on my axes for one thing, but it's still the same picture for the most part. So, do I have any domain issues with the original function? I would have issues if there was anywhere here between -2 and 6 where this did not exist, where it was not defined, that was outside the domain. If I had a quotient that was not defined somewhere in there, that would be an issue because it would not be continuous. But because this is continuous for all real numbers, it's definitely continuous over any interval, basically. But the question has to involve a closed interval because I have to have endpoints to be able to finish the problem. So let's start with our derivative. Walk me through.
12x cubed. 24x. 96x.
Minus
96x.
96x and then nothing. Ooh, I have a cubic. What's the most number of times a cubic can equal 0? 3. The degree of it's always the most number. I might have a repeated factor, but in this case I won't, so I should get 3 critical values here. Nice. Okay, and you can all factor that in instantly, right? Oh, but wait a minute. Wait a minute. Every term has an x. Is that a good thing? Well, that's a really good thing. Do I have a common factor?
12.
Cool. X, and what will that leave me with?
1.
How about x squared?
2x.
8. Minus 8. Does that factor? I think it does. I'll do my part. There. That's my contribution.
Plus 4 minus 2.
+4 minus 2, and always double check. Yeah. Oh, beautiful. And this will equal 0 at when? X equals,
-4.
careful,
Oh, yeah.
0.
0. Ooh, might we forget that one? Yeah, a lot. That's why I could already tell we were going to forget it. I'll say, or X equals,
-4.
or X equals
2.
2. Well, do you like all of those answers?
No.
Which one don't you like?
-4.
Here's what we're gonna do. Here. Why am I crossing it off?
Because it's outside the interval.
Because it's not in the interval. It's outside the domain that we're considering for our final answer. Ah, this is the first instance where this has actually come up. I have a value, I did everything right, but I cannot consider that for an answer because it's outside the domain of what we're working with. When we get to the application problems, and we're saying, we produce widgets, and here's, the interval that we can produce, and my answer's outside that interval, then the answer's impossible. So you have to know the domain before you start, because if your answer comes from a number outside the domain, it can't be an answer. So the word we use, we'd say x equals -4 is an extraneous solution. It answered that question, but it does not apply to this problem. We correctly did that. It would be a mistake to not put it here, because it makes it look like you didn't factor correctly. No, cross it off because it's extraneous. Because if I widen that interval, might I have considered that one?
Yes.
Yeah. So it solves the equation, but I'm not using it. So I need to now calculate a few values. I am now going to calculate f of 0, f of 2. Is that it? No. I'm also going to consider f of -2 and f of 6. I'm considering every critical value in the interval. That's the most important part. Every critical value in the interval, and I'm considering my endpoints. And here's my money back guarantee. I have no idea what the answer is, but I can absolutely guarantee you that the high and the low will come from one of those four. I can't tell you ahead of time. You got to calculate them. All right, I'll do the first one. Okay, you guys have calculators, right? Let's do all of them. Everybody pick a different one, so I need confirmation. Anybody got this one? You're all doing top down, not bottom up.
I did say-
What'd you get for that one?
The same, 38.
No, this
oh,
one, this
sorry. I was confirming, but I...
Everybody was going after the first one.
-2.
Is that what you got? Negative, negative or positive?
Negative.
Negative? Okay. Anybody got f of 2?
-83.
Negative 83.
Negative 80. Does everyone agree with that?
Yeah.
Well, is the choice easy now? The question was to identify the absolute maximum and absolute minimum over this closed interval. Safe? Which is the most negative?
-2 and 11.
Actually, this one isn't it? Interestingly enough, my answers occurred at the endpoints in this case. There's no rule. You cannot predict ahead of time. So now let's draw this and see what we just said. Okay? because I do want to tweak the problem. Oh, whoa, what did you just do over here? Next. Oh, there we go. All right, back a little bit. All right, so what I'm gonna do is change the Y scale just a bit. What was our most negative? It was negative 211. So let's go negative about 300 to positive, I don't know, 4,000. Oh, that's pretty good. Okay. Let me see if we can do it. Maybe it's the magic is gone. All right, not gonna be able to do that, so let's do this. I think you can all see this well enough, am I right? Okay, so what did we just do? I changed the scale. You notice my y-axis scales into the thousands. One of the things I always remind people, even in remedial algebra, you know, if one square is 1 unit in one direction, one square is 1 unit, that's fine, but in reality it's almost never going to be the case. Maybe you're counting by ones this way and by thousands this way, or by 0.1 this way, and you know, the x-axis scale and y-axis scale, because they're different units, don't have anything to do with each other. So I counted by a lot. So what did we just do? We did f of -2, negative 211, f of 6, way the heck up there. Okay? I want to change one thing. I'm going to change one thing. I'm going to widen my interval now, -5. Because I want you to see something, because I don't want you to get a false sense of what we just did. Everything we did was true and correct, and our answers came from the endpoints. I now want to widen it from -5 to 6. If I widen it from -5 to 6, there's two major changes. I'm now going to include the -4. Agreed? What else? I'm going to throw this one out. So now let's do f of -4 and let's do f of -5, shall we? I'm making one change. This is a brand new problem. I'm widening my interval to see what does that do to our answer. I got -515 for that one. I think that looks pretty accurate. I'm going to eat this. And I got -328. Anybody else get those numbers?
Yeah.
Okay, so I widened my interval a little bit, which now means I had 3 critical values to consider, as well as the 2 endpoints. I'm not going to shorten the right side, I just wanted to widen it. So, whereas before, we went from here, sorry, it's way up there. We went from here to here, and clearly that's the low and that's the high. Now I'm going from here to up there. Now that's the low, isn't it? Can everyone see that? That's now the low. So this would be the absolute minimum. My absolute max would still be the same because I only changed that one thing. But now my absolute minimum occurred at a critical value. My max occurred at an endpoint, my min occurred at a critical value. Is it possible that I could bring the right side in so much that that ends up being the maximum? Is that possible? Yeah, what if I brought the right side all the way to here? So the point being, you can't possibly predict what the answer is going to be. You're finding the critical values. You're now evaluating the endpoints and saying whoever wins, wins. I brought the picture so we could see what we just calculated, how it coincided with the picture. But the picture wouldn't have helped me get any of these values. The picture just confirms that we did everything right, after the fact. And that's kind of the way I'd like you to think of things. I really do want you guys to have access to pictures when it's graphing related, because think of the first two problems we did today. We found the critical values, we were trying to figure out maxes and mins, particularly the one involving the roots. We did everything right, but we have no feel for what that picture looks like. So I plotted a few points and graphed it. That's all I really needed to do. But then going to the technology and saying, oh good, I graphed it correctly, I interpreted it correctly, I can clearly see the max and or min right there. Because things can only get more complicated. We're always going to do the mathematics, and then we're going to see if the picture confirms it. See, the other thing you have to understand, I'm reverse engineering these so the numbers come out nice. If I said, everyone here just randomly make up a quadratic, just make up a simple parabola, chances are most of our vertices are going to occur at irrational coordinates. They're not going to occur at nice, happy values. They're going to occur at horrible values. You actually have to reverse engineer it to make it occur at a nice value. So generally speaking, if you have a graph, in general, the highs and lows are not going to occur at integer values. Why would they occur at integer values? They occur wherever they occur, which is far more likely to be an irrational number. Oh, right, I can't just plot points and find that. I can't look at a graph and tell you where that is. It's between integer values. So we have to have a way of finding it in general. So extreme value theorem, simple terms. I figure out the domain of my overall function, and then the interval I have has to be continuous over that interval, and the endpoints have to exist. They have to be defined. There can't be weird stuff. There can't be removable discontinuities. I can have no asymptotes in the middle of the interval. Nothing weird like that. Okay? I could be weird in the middle of an interval. We'll do another one now. Let me erase this. Or blank this out. Okay. We're introducing this as it applies to graphs, but it turns out to be one of the most powerful tools when we start solving problems. My Calc 3 class on Wednesday of next week is going to do a version of this and the optimization in 3D that's extremely, extremely powerful. And in that class, I come back and I review what we do in this class in our optimization lecture, and then take it on to higher dimensions. Everything we do in Calc 3, we always come back to Calc 1 and say, here's what we did in Calc 1, now let's tweak it. So if you don't remember the Calc 1, it does make it harder, but I always review, I don't reteach the Calc 1, I review what we did in Calc 1 and say, now that we've introduced more variables, here's how things change. So we want to get it right, obviously, the first time around. Let's take the one we did earlier. Okay. Did we already find the critical values on this one? What were the critical values we found earlier?
X equals 2.
There were two values.
X equals 2 and 0.
And they were both in that interval? Yep.
Yeah.
So how many calculations do I need to do to answer this question? 4. These two, these two. The most common mistake we make as a group is we will only do one of those pairs. We'll either do the critical values or we'll do the endpoints. We'll forget the other one. That's very, very common. People forget. No, all the critical values in the interval and the endpoints. Remember, we said this is defined for the whole number line. And it is continuous over the whole number line too. We have one weird place where it's not differentiable, but that wasn't important. Okay, that wasn't going to prevent us. So, I think, by the way, if you have your table of values, I think we have all of these already. Maybe we don't have -2, but I think we have all the other ones. Now, if I want to write these without decimals, well, that's a 0. This would be 2 to the 2/3, or you could also say cube root of 4. So this is -3 times the cube root of 4. Now, for graphing purposes, I would definitely give you a decimal, but that's what the answer is. At -2, it's also cube root of 4, but times -7. And at +4, it's the cube root of 16 times -1. Now, I can't easily compare those last three, but I can tell you something. How do I know that's my absolute max?
Everything else is
Everything else is negative, yeah. Zero's the biggest it ever gets, yeah. Yeah, it's kind of sad. All right, well, I need to calculate those other guys. What did we get approximately as a decimal for this one?
-4.7.
-4.8.
8.
This was approximately -4.8. We didn't do this one. This was outside the range, so we still need to do that one. I'm guessing it's going to be more negative right now.
-11.11.
11 point.
11.
That was one. And then the last one.
-2.5.
Okay, who wins? That guy wins? So my absolute max came at a critical value. My absolute min in this case came at an endpoint of the interval. Okay, that's probably the most common scenario, is that an endpoint will produce one of the answers, a critical value will produce the other. That's actually really common. They can both come from endpoints, they can both come from critical values. There's no rule. One of each is probably the most common. Now, could we change that interval like we did before? Yeah, we keep changing it, we keep getting different answers, but so that's it. So the extreme value theorem says that an absolute minimum and absolute maximum are guaranteed to occur if the function is continuous over the interval and the endpoints exist. Okay? That seems like a minor thing, and rarely will we run into issues with that. That's not really going to be a problem. Where the problem would be is if I gave you a function that had a discontinuity, and the discontinuity occurred in the interval. So let's start with a really simple one. Let's keep it really simple. F of x equals 1 over x. And I want the interval from 1 to 4. Am I going to have an absolute maximum and an absolute minimum over that interval? Well, what's the domain? Hold on, go backwards. What's the domain of this?
On and on except 0.
Yeah, so I'll write it like this. 0 is not in that interval. So am I okay? Yes, I am okay. So f prime of x equals -1 over x squared, which is never 0. It's undefined at 0, but 0 is not in my domain. So do I have any critical numbers for this? Right, do I have any critical numbers? There's no horizontal tangent, but there's also none of the weird ones because the domain does not include 0. So the only interesting thing for the derivative is at 0. That's not in the domain. There are no critical values. Oh, so what am I going to check then?
Endpoint.
Just these two. So f of 1 is 1. F of 4 is 1/4. So there's the absolute max. There's the absolute minimum. Kind of boring. So we chose this portion. That was our high, that was our low. Now, how could I really mess you up on this? Now, this is where you got to be paying attention. All right, I'd like you to find the absolute max and min over this interval. Now, what did I just do? I said from here to here, didn't I? Is there a high? No, it goes forever. Is there a low? No, it goes forever. But wait a minute, I thought I was guaranteed infinity is not a max. It's not a value, right? It's a destination. Would you agree there's no absolute max or absolute min in this case? So, wait a minute, I thought the extreme value theorem guaranteed both. Why does it fail?
It's not continuous, it's not continuous.
Because I'm not continuous throughout this interval. I have a discontinuity, 0. Oh, okay, so the discontinuity messes everything up. It means that it doesn't apply at all. I had to be continuous between the endpoints. I'm not continuous at 0. So it fails. I can't use it. Now, I'm not trying to trick you, I'm just saying this is what happens when you don't meet the criteria. So the theorem, I told you the hypothesis. I am continuous over an open interval and the endpoints exist. That's the hypothesis. The conclusion is you are guaranteed an absolute max and an absolute min. Can I have more than one max? You coach a basketball team. Can you have more than one player be the tallest player on the team? No. But could you have more than one player that are the same height?
Yeah.
Oh. I cannot have more than one maximum. I can have one maximum, but can it occur at more than one point? Yes. Don't confuse the two. My maximum is 10 and my maximum is also 20. No, 20 I think will win, right? I have a maximum of 10, but it occurs at 5 different places. That's okay. That's weird, but it's okay. So the maximum value is the highest height, period. There can only be one number that's the highest number. It can occur more than once, like the sine wave. Okay? Do you see where we can get a little bit confused on that? I can't say the two different values. Now, go back to what we did the first half of class today. You can have as many relative maximums as you want. What do I mean by as many as I want? I'm going to draw an ugly graph that you guys will not have to worry about for several more semesters. Several more semesters. This is called harmonic motion. The fact that it's getting smaller is called damped harmonic motion, really bad shock absorbers. It oscillates, but what's happening to my oscillations? It's getting smaller, smaller, smaller. Does it ever end, actually? It goes forever. So how many maximums am I going to have? Infinitely many, and every one of them is going to be different. And they're getting closer to 0 as I go. How many mins am I going to have? Infinitely many. Will I have an absolute max? Will I have an absolute min? Will I have local maxes? Yeah. All the rest. Local mins? All the rest. There is no upper limit to how many local extrema you can have, but you can only have one absolute. This is the most absurd example I can come up with that explains all of that at one time. You can only have one absolute max, you can have infinitely many relative. That's what that would look like. Now, you're not going to do that one, don't worry. But that's essentially a sine wave that's getting smaller and smaller and smaller as you go. Okay? Everybody cool with that? How would you make a sine wave get smaller and smaller and smaller? You throw an exponential function in front of it. In other words, e to the negative x times sine x. That'll make it get smaller. Okay, that's one of the things we do. You know, it's crazy. But this now becomes a very important problem, let's say, in like physics and other areas, that I understand that. Okay? It's an oscillation that is getting smaller and smaller and smaller, but the point being, I can tell you where all the maximums and minimums occur. I can tell you what the values are. Now, if I gave you any closed interval over that, would there be one absolute max and one absolute min? Yeah, and it won't necessarily be the original ones because it depends on where my interval is. This one's starting at the origin. What if my interval starts here? What do you think?
It's larger.
Am I continuous over the open interval? I'm not even defined over the open interval. Yeah, you can't be outside the domain. The domain of a function is the lowest level of security you need. What can I actually insert into my function? Now, where is it continuous? That's a little bit stronger criteria. Where is it differentiable? That's the highest criteria. I can have a cusp. I'm not differentiable, but I am continuous. This only required continuity. The next theorem we're going to look at, which I believe is next day, called the mean value theorem, I have to be differentiable for it to work. If I'm not differentiable, it will fail. Today, I only had to be continuous. I can't have holes. I can't have breaks. I can't have vertical asymptotes. I just have to be able to drive from point A to point B. Literally, I just have to have a road that doesn't, cave in somewhere. Questions? Good? All right, I think we're at a good stopping point. We're actually a little bit on the early side, so go ahead and press that.